Okay, so have you ever, looked at a giant pile of puzzle pieces and felt kind of overwhelmed?
Yeah, totally.
That's kind of what it feels like sometimes trying to wrap your head around data science, right?
I get it for sure.
But that's what this deep dive is all about. We're going to dig into this book, Data Science and Machine Learning, mathematical and statistical methods, and hopefully uncover those aha moments, you know?
Absolutely. And you know what I appreciate about this book?
What's that?
It starts with something so basic, but so crucial. Understanding your data.
It's like laying the foundation before you build a house, right?
Exactly. You can't build on a shaky foundation.
No way. So are they talking about different types of data right off the bat?
Yeah, they dive straight into it. They talk about qualitative data, like describing something with words, like tall or short. And then you've got quantitative data, which is all about numbers. That can be discrete, like counting how many people are in a room,
Okay.
or continuous, like measuring someone's exact height.
So how does that actually affect how we analyze data, though?
That's a great question.
Hmm.
And it's something the book emphasizes a lot. You have to visualize and analyze data according to its type.
So it's not a one-size-fits-all approach?
Exactly. Remember that abalone data set they mentioned?
Oh, yeah, the one where they're trying to predict the age of those sea snails?
Yes, that's the one. They use that example to show how visualization techniques have to be tailored to the type of data you're looking at.
Can you give me an example?
Sure. So when they were comparing the number of abalone in different age groups, that's discrete quantitative data, right?
Right.
They used a simple bar plot for that.
Makes.
But when they were visualizing the distribution of abalone shell weights,
Yeah.
which is continuous quantitative data, they used something called a kernel density estimate. It gives you a smoother curve to represent how the data is spread out.
So it's like choosing the right tool for the job.
Exactly.
Yeah.
A bar plot for categories, a kernel density estimate for understanding the shape of continuous data.
And why is it so important to choose the right visualization method?
Because the wrong method can actually be misleading.
Oh, wow.
Imagine trying to understand the distribution of heights in a population, but you only use a bar plot. You'd miss out on key information about the data's shape, like is it symmetrical or skewed to one side.
That makes sense.
So yeah, understanding these different data types and visualization technique is about making sure we're getting a clear and accurate picture of what the data is telling us.
It's about asking the right questions and getting the right answers.
Exactly. And that leads us to another fundamental concept the book highlights: the difference between supervised and unsupervised learning.
Okay, let's hear it. Okay,
Right.
so we've got our data visualized and we kind of get what type it is.
Right.
But how do we actually start making sense of it all, you know?
Oh, that's where the fun really begins. The book introduces us to the world of learning algorithms.
Learning algorithms sounds complicated.
It's not as scary as it sounds.
Yeah?
Think of them like tools for uncovering hidden patterns and making predictions from data.
Okay, so like a detective's magnifying glass.
Exactly. And these algorithms are divided into two main categories: supervised and unsupervised learning.
I've heard those terms before, but I'm a little fuzzy on the details.
No worries. So supervised learning is like having a teacher guiding you. You've got labeled data, meaning each data point comes with the correct answer already attached.
So it's like we're giving the algorithm the answers in advance.
In a way, yeah. The algorithm's job is to learn from this labeled data and figure out how to predict the answer for new data it hasn't seen before.
Okay, so it's like if you showed a kid a bunch of pictures of cats and dogs and told them which ones were which, then hopefully they could start identifying new cat and dog pictures on their own.
That's a perfect analogy.
Mm-hmm.
And the text gives some specific examples of supervised learning techniques, like linear regression, for instance.
Linear regression, that rings a bell.
It's a way to model the relationship between two variables. Let's say you're trying to predict a student's exam score based on how many hours they studied. Linear regression tries to find the best straight line that represents that relationship.
So if we plotted all the data points for study hours and exam scores on a graph,
Right.
linear regression would try to draw a line through those points that's as close as possible to all of them.
You got it. And once you have that line, you can use it to predict the exam score for a new student based on how much they studied.
That makes sense.
But it gets even more interesting. The text doesn't just stop at linear regression. It introduces us to more complex techniques, like polynomial regression.
Polynomial regression. So is that like linear regression but with curves instead of just straight lines?
Exactly.
Right.
It lets us model more complex relationships between variables, like maybe studying a little bit gives you a big boost in exam scores, but then studying even more starts to have diminishing returns.
Yeah. So it's like fitting a curved line to our data points instead of just a straight line.
Precisely. And the book emphasizes how important it is to evaluate how well these models actually fit the data.
Because we don't want a model that's too simple and misses important patterns, right?
Right. We also don't want a model that's too complex and overfits the data.
Overfitting. What's that?
It's like the model is memorizing the training data so well that it doesn't perform well on new data.
Ah. So it's like studying for an exam by just memorizing the textbook.
Hmm.
You might ace that specific test, but you won't really understand the material.
Exactly. And that's where techniques like cross-validation come
Yeah,
in.
cross-validation. That sounds familiar.
It's like having multiple mini-tests for your model. You split your data into chunks. Use some chunks for training and others for testing.
So you're basically checking to see if the model can generalize to new data that it wasn't trained on.
Exactly. It helps us avoid that overfitting problem we were talking about.
Clever.
Now, shifting gears a bit, let's talk about unsupervised learning. This is where things get really interesting, because now we're dealing with unlabeled data.
So there's no teacher guiding us anymore.
Exactly.
Hmm.
We're giving the algorithm that pile of puzzle pieces, but this time there's no picture on the box to guide us.
Sounds challenging.
It definitely can be. In unsupervised learning, the algorithm's job is to find its own patterns and structures in the data. Clustering is a classic example.
Clustering, like grouping things together.
Exactly. Imagine you're an online retailer and you want to understand your customer base better.
Mm.
You could use clustering to group customers with similar purchasing habits together.
Okay, so instead of telling the algorithm up front how to group the customers like by age or income level,
Huh.
we're letting the algorithm figure out those groupings based on the patterns it sees in the data.
Exactly. And this can lead to some really valuable insights.
Yeah.
You might discover groups of customers that you never even knew existed. And then you can use that information to tailor your marketing campaigns, recommend products, and improve the overall customer experience.
It's like uncovering hidden gems in your data.
Exactly. And that's just one example of the power of unsupervised learning. There's a whole world of other techniques out there, each with its own strengths and applications.
So we've got supervised learning where the algorithm learns from labeled data and unsupervised learning where it uncovers its own patterns in unlabeled data.
You got it. It's like having a whole arsenal of tools for tackling different types of data analysis challenges.
And the best tool for the job depends on the specific problem we're trying to solve.
Precisely.
So we've covered supervised and unsupervised learning.
Right. Two powerful branches of machine learning.
But the book doesn't stop there, does it? It goes on to this whole other family of techniques called Monte Carlo methods.
And this is where things get really interesting. Monte Carlo methods are all about using randomness to solve problems.
Randomness. I thought in data science we were trying to get rid of randomness, not embrace it.
Well, it might seem counterintuitive, but sometimes randomness can be a really powerful tool, especially when we're dealing with problems that are too complex to solve directly.
Okay, I'm intrigued. Can you give me an example?
Sure, imagine you're trying to figure out the area of a really weirdly shaped pond. Like it's got all these curves and inlets. It would be really difficult to measure the area precisely with traditional geometry, right?
Ah, I could see that.
So instead of trying to measure every single nook and cranny, we can use a Monte Carlo method. We can randomly throw a bunch of darts at the pond surface.
And then just count how many darts land inside the pond versus how many land outside?
Exactly. And if we know the total area we threw the darts at, we can use that ratio to estimate the pond's area.
So we're basically using randomness to approximate the answer.
Precisely. And that's the basic idea behind Monte Carlo integration. The text gives a great example of how this technique can be used to estimate complex integrals, things that would make even seasoned mathematicians sweat a little.
So instead of trying to solve those integrals directly, which could be really difficult, we can use randomness to get a pretty good estimate.
Exactly. And the beauty of Monte Carlo methods is that they can be applied to a wide range of problems, not just calculating areas or integrals.
The text also mentions something called importance sampling. What's that all about?
So with importance sampling, instead of just throwing our darts randomly, we can be more strategic. We can focus our throws on certain areas that we think are more important for getting an accurate estimate.
So going back to our pond example, it's like if we knew that one side of the pond was much bigger than the other, we'd want to throw more darts on that side to make sure we're getting a good representation of the overall area.
Exactly. It's about being smart about how we use randomness to get the most accurate estimate possible.
And then there's Markov chain Monte Carlo, or MCMC for short. What's the deal with that?
Ah, yes, MCMC. That's a whole other level of Monte Carlo awesomeness. These methods are like taking a random walk, but with a purpose.
A random walk with a purpose. I like it. So instead of just wandering around aimlessly, we're guided by something.
Exactly. We're guided by probabilities. MCMC methods allow us to explore complex probability distributions, which is like understanding the likelihood of different outcomes. And they're particularly useful in Bayesian statistics.
Bayesian statistics. Now that's a whole other can of worms.
It is a fascinating can of worms, though. But for now, just know that MCMC methods are like having a special set of tools for navigating the world of probabilities. And the text highlights two specific MCMC algorithms, the Metropolis-Hastings algorithm and Gibbs sampling.
So these algorithms help us make sense of probabilities in a more systematic way.
Exactly. And speaking of Bayesian statistics, the text also raises an important point about the trade-off between model complexity and interpretability.
So it's like that saying, sometimes the simplest explanation is the best.
Exactly. We could build incredibly complex models with tons of parameters that capture every little nuance in the data.
But those models might be so complicated that even we as data scientists have trouble understanding why they're making certain predictions.
Exactly. It's like having a black box that spits out answers, but you have no idea how it got those answers.
And that can be a problem, especially in fields like healthcare or finance, where we need to be able to understand and explain the reasoning behind our model's predictions.
Absolutely.
Yeah.
So the text emphasizes that it's not always about building the most complex model possible. Sometimes a simpler, more interpretable model is actually the better choice.
Even if it means sacrificing a little bit of accuracy.
Exactly, because ultimately it's about finding the right balance between accuracy and interpretability. The model that best meets the specific needs of the problem we're trying to solve.
It's about making informed decisions based on the data and the tools we have available.
Precisely. And that brings us to the end of our deep dive into data science and machine learning, mathematical and statistical methods.
Wow, we've covered a lot of ground. From different data types and visualization techniques to the nuances of supervised and unsupervised learning, and even the mind-bending world of Monte Carlo methods.
We've explored some of the most important tools and concepts in data science. But remember, this is just the beginning. The world of data is constantly evolving, and there's always something new to learn.
So, to our listeners out there, stay curious, keep exploring, and never be afraid to ask why. Because the more you learn about data, the more you realize how much more there is to discover.
And who knows, you might just uncover the next groundbreaking insight that changes the world as we know it.
Well said. And on that note, thank you for joining us on this deep dive into the fascinating world of data science and machine learning.
It's been a pleasure exploring these concepts with you.
Until next time, keep those data fires burning.